The smoke rose through the curved stone ceiling of Lars Anderson's underground chamber while his neighbors' meat rotted in their wooden sheds after just 3 weeks. What they had mocked as a waste of effort, a dome carved into the earth with stone walls and ceiling lamps burning during the smoking process, would keep his family fed for 8 months while theirs starved through the long Dakota winter. Before we begin, let us know where you're watching from, and if stories of frontier ingenuity like this inspire you, hit that subscribe button. Tomorrow's tale is even more remarkable than this one. The winter of 1856 killed more settlers in Dakota Territory than any season before it. The cold arrived in early October, 2 months earlier than anyone expected, and it brought temperatures that dropped to 40 degrees below zero on clear nights. But the cold itself was not what destroyed families. It was the thaw that came in late November, unseasonably warm days that melted snow and raised temperatures into the high 30s, only to plunge back below zero within hours. That freeze-thaw cycle, repeated 3 times before true winter set in, destroyed the food supplies that families had worked all summer to preserve. Smoked meat that had seemed perfectly cured turned rancid within days. Root cellars flooded and then froze, destroying vegetables. Families who had felt secure in September were facing starvation by December. Lars Anderson lost his younger brother that winter. Eric had settled his own claim 3 miles west of Lars's homestead. He had built everything the same way the other Norwegian immigrants built: a sod house, a small barn, a wooden smokehouse for preserving the hog and deer meat that would sustain his family until spring. Eric had 5 children, the youngest only 2 years old. When the first thaw came in November, Eric's smokehouse did what smokehouses did. The wooden structure absorbed moisture from the humid air. The temperature inside rose with the outside temperature. The meat, which had been cold and dry, became warm and damp. Bacteria that had been dormant began to multiply. By the time the temperature dropped again, the damage was done. The meat looked acceptable on the outside, but inside it was already spoiling. Eric's family ate that meat through December because they had nothing else. By January, 3 of the children were sick with what the settlers called meat poisoning. By February, Eric's youngest daughter was dead. The other 2 children survived, but they were weakened in ways that would affect them for years. Eric himself never recovered from the guilt. He had done everything right by the standards of the community. He had worked hard, prepared carefully, followed the methods that had sustained Norwegian families for generations. But those methods had been developed in a different climate, with different weather patterns. They did not account for Dakota's brutal freeze-thaw cycles. Lars buried his niece on a hill overlooking Eric's claim. The ground was frozen solid. It took him 2 days with a pickaxe to dig a grave deep enough. During those 2 days, he thought constantly about preservation. He had lost meat to spoilage himself that winter, though not enough to threaten his family's survival. His smokehouse had performed slightly better than others, but only because he had built it more carefully, with tighter joints and better ventilation. It still could not handle the temperature swings. No wooden smokehouse could. Standing at his niece's grave, Lars realized something that would consume him for the next 8 months. The problem was not the meat itself, or even the smoking process. The problem was temperature. Every preservation method settlers used depended on keeping food consistently cold and dry. But Dakota Territory offered no consistency. October could bring summer heat or winter blizzards. November might swing 40 degrees in a single day. December could stay frozen for weeks, then suddenly thaw. January was the only reliable month, frozen solid from start to finish. February began the cycle again, warm days mixed with Arctic cold. March was chaos, freezing at night and melting during the day. April continued the pattern until true spring arrived in May. Wooden smokehouses could not handle these swings. When the temperature outside rose, the temperature inside rose. When humidity increased, moisture penetrated the wood and reached the meat. When the temperature dropped again, that moisture froze, creating ice crystals that damaged meat fibers and accelerated decay when the next thaw arrived. The smoking process itself helped. Smoke contained compounds that inhibited bacterial growth and created a protective coating on meat surfaces. But smoking alone was not enough if the meat experienced repeated temperature cycles. Lars had watched neighbors lose entire winter supplies. He had seen families ration spoiled meat because they had nothing else. He had watched children get sick and adults weaken. The community accepted these losses as inevitable, part of the cost of frontier life. But Lars could not accept inevitability, not after burying his niece. He began studying how other settlers stored food. Some dug root cellars underground, using earth as insulation. These cellars worked well for vegetables and dried goods because they stayed cool and relatively stable. But they were too damp for meat. The earth walls released moisture constantly. Meat stored in root cellars absorbed that moisture and spoiled quickly. Other settlers built ice houses, cutting blocks from frozen lakes and storing them underground, packed in sawdust for insulation. Ice houses worked during summer, keeping food cold when outdoor temperatures soared. But they required enormous labor to fill and maintain. The ice melted gradually, creating water that had to be drained. By late summer, the ice was usually gone, and ice houses did nothing to solve the winter preservation problem. The issue was not keeping food cold in summer. It was keeping food at a stable temperature during winter's freeze-thaw cycles. Lars talked to every old-timer he could find, men who had survived multiple Dakota winters. They all said the same thing. You built the best smokehouse you could, you smoked your meat thoroughly, and you hoped for a cold winter with few thaws. Hope was not a strategy Lars could accept. There had to be a better way. He simply had not discovered it yet. But he would. He had all spring and summer to figure it out before the next butchering season arrived in October. Lars spent March and April thinking about temperature stability. Wood responded quickly to air temperature changes. That was its fundamental weakness as a building material for food storage. Earth responded slowly. A foot below the surface, soil temperature lagged behind air temperature by days. 2 feet down, the lag increased to weeks. 3 feet down, temperature barely changed at all, holding steady around 45 to 50 degrees year-round in Dakota Territory. Lars had observed this in root cellars. Even during summer heat waves, the air 3 feet underground stayed cool. Even during Arctic cold snaps, it never froze solid. The earth itself was a massive thermal stabilizer, absorbing temperature extremes and maintaining equilibrium. The problem with existing root cellars was moisture. Earth walls constantly released water vapor, especially when outside temperatures rose and fell. That moisture had nowhere to go in an enclosed space. It condensed on food, walls, ceiling, creating the damp environment where meat spoiled rapidly. But what if the walls were not bare earth? What if they were lined with something that blocked moisture while still benefiting from the earth's thermal mass? Stone was the obvious answer. Stone absorbed almost no moisture. Stone could be shaped and fitted to create a sealed surface. Stone absorbed heat slowly and released it slowly, adding to the thermal stability that earth provided. A chamber dug into earth and lined with stone would combine the best properties of both materials. Lars began sketching designs in the margins of his almanac. A simple rectangular room would be easiest to build, but it would have problems. Corners created dead air spaces where smoke would not circulate effectively. A rectangular roof would need support beams, and those beams would drip condensation. Water always condensed on the coldest surface in any space. In a rectangular room, the ceiling was the coldest surface, because heat rose and cold air sank. Condensation dripping on meat would cause exactly the spoilage he was trying to prevent. But a curved ceiling changed everything. A dome or barrel vault shape had no corners for dead air. Smoke would rise naturally, and spread evenly across the curved surface. And condensation would not drip. It would run down the curve to the walls, away from the hanging meat in the center of the space. Lars had seen earth-sheltered buildings in Norway, though not many. His grandfather had described old food storage chambers built into hillsides, with stone-lined interiors and arched roofs. Those chambers had lasted centuries. They kept food cool in summer and prevented freezing in winter. They were built for a different purpose than smoking meat, but the principles were the same. Stable temperature, controlled moisture, enclosed space. If he could combine an earth-sheltered chamber with a proper smoking system, he might solve the preservation problem that killed his niece. The concept was clear in his mind now. The challenge would be execution. When Lars began explaining his plan to other settlers, the reactions ranged from skepticism to outright mockery. His neighbor, Olaf Henriksen, listened patiently while Lars described the underground dome concept, then shook his head slowly. "You want to dig a cave, line it with stones, and smoke meat in the dark like a troll?" Olaf said. "Lars, we have perfectly good methods. Build your smokehouse with thicker walls if you are worried. Double the boards. That will stop temperature swings." Lars tried to explain that wood thickness made little difference when the temperature changed 40 degrees in one day, but Olaf was not interested in explanations. He had survived 6 Dakota winters using a standard smokehouse. That was proof enough for him. Others were less diplomatic. Anders Gunderson, who had lost meat to spoilage, just like everyone else, called the idea wasteful. "You want to spend the entire summer digging a hole, hauling stones, and building something that might collapse and bury you? For what? So your meat stays fresh an extra week or two? Not worth the effort." Lars pointed out that his niece had died from spoiled meat, and that seemed worth preventing. Anders looked uncomfortable, but did not back down. "That was tragic, yes, but building a cave will not bring her back. You should focus on helping your brother recover, not chasing impossible ideas." The word impossible appeared in multiple conversations. An underground smoking chamber was impossible because no one had built one successfully in Dakota territory. It was impossible because the effort required was too great. It was impossible because if it actually worked, someone would have done it already. The criticism bothered Lars less than the certainty behind it. These men were not stupid. They were experienced settlers who had survived conditions that killed others. But they could not imagine solutions outside their existing knowledge. They had built wooden smokehouses in Norway, so they built wooden smokehouses in Dakota. When those smokehouses failed to handle Dakota's climate, they accepted the failures as inevitable rather than questioning the methods. Lars understood that thinking. He had shared it until his niece died. Tragedy had given him permission to question everything. He no longer cared if an idea seemed impossible. He cared if it might work. By late April, Lars had stopped discussing his plans with neighbors. He would build his earth-sheltered smoking chamber and let the results speak for themselves. If it failed, he would learn from the failure and try something different. If it succeeded, others would see the proof and perhaps build their own. But he would not waste time arguing about theory. He had land to prepare, stones to gather, and a dome to excavate before the fall butchering season arrived. The work would take every spare hour between spring planting and fall harvest. He had no time for convincing skeptics. Lars chose his construction site in early May after the ground had thawed enough to dig test holes. The location was crucial. Building underground meant working with drainage, soil composition, and structural stability. A poor site would flood, collapse, or require so much reinforcement that the project would become impossible. He spent 3 days walking his property, studying the terrain with new eyes. He had farmed this land for 4 years, but he had never considered it as potential building space beneath the surface. The best location revealed itself on the southern slope of a low hill about 60 yards from his main house. The hill was not dramatic, rising only 15 feet above the surrounding prairie, but that elevation mattered. Water flowed downhill. A chamber dug into the hillside would naturally drain rather than collect water. The southern exposure meant maximum sunlight during winter, which would help keep the entrance area clear of snowdrifts. Lars dug 5 test holes across the hillside, each 3 feet deep, studying the soil layers and watching how quickly groundwater seeped in. The top 18 inches were dark topsoil, rich and loose. Below that, he found 2 feet of dense clay, yellowish-brown and sticky when wet. Beneath the clay, the soil became sandier, mixed with small stones. This layering was ideal. The clay layer would form the bulk of his dome structure. Clay held its shape when carved. It could be compacted and smoothed. It was naturally waterproof when properly managed. The sandy layer below would provide drainage, allowing any moisture that did penetrate the clay to flow away rather than pool beneath the chamber. The topsoil layer on top would support the sod covering that would insulate and disguise the structure. He marked the entrance location with stakes, positioning it to face southeast. This orientation gave him morning light and protection from the prevailing northwest winds that dominated Dakota winters. The chamber itself would extend into the hillside, carved from the clay layer. He calculated dimensions carefully. Too small, and the smoke would be too concentrated, potentially making the meat bitter. Too large, and he would waste months of digging for space he did not need. He settled on a chamber 12 feet in diameter and 8 feet high at the center of the dome. This would give him roughly 100 square feet of floor space and enough height to hang meat on multiple levels without the lower racks being too close to the smoke source. The dome shape would be his greatest construction challenge. Digging a rectangular room was straightforward. You removed earth in straight lines and flat planes. A dome required constant attention to curvature. Every shovelful had to maintain the arc. But Lars had seen dome construction before. Norwegian farmers occasionally built small dome-shaped storage huts using turf. The principle was simple. Start with a circular floor plan. As you build or dig upward, each successive layer becomes slightly smaller in diameter, creating an inward curve that eventually meets at a central point. Gravity makes the shape stable. Each stone or each section of carved earth supports the sections around it. The arch distributes weight outward and downward, not straight down like a flat roof. Done correctly, a dome was stronger than any rectangular structure of similar size. Lars began digging on May 10, 1856. He rose before dawn, completed his essential farm chores, then worked on the chamber until early afternoon when the sun made labor dangerous. He returned to farm work in the evening, caring for animals and maintaining equipment. This schedule gave him 4 to 5 hours of excavation daily. The work was brutal. He started by removing the topsoil from a circular area 15 feet in diameter, 3 feet larger than his planned chamber. This would give him working room around the entrance and space for the doorframe structure. The topsoil came out easily with a spade, piling up beside the excavation site. He would use it later for the final covering. Then he reached the clay. Clay did not cooperate with shovels the way loose soil did. When dry, it was hard as poorly fired pottery. When wet, it became slippery and heavy, clinging to tools and making progress exhausting. Lars learned to wet the clay slightly before digging, just enough to soften it without making it muddy. He used a pickaxe to break the clay into chunks, then a spade to remove the pieces. Each swing of the pickaxe jarred his shoulders and back. Each shovelful of wet clay weighed twice what dry soil weighed. By the end of the first day, he had removed roughly 2 cubic yards of material. At that rate, excavating the entire chamber would take 6 weeks, assuming the work did not become more difficult as he went deeper. The excavation did become more difficult. As Lars dug further into the hillside, he had to remove material from an increasingly confined space. The first few feet were manageable. He could stand outside the hole and throw earth outward. But once he was 4 feet deep, he had to work inside the excavation. He built a wooden ramp leading up to the surface. Using planks he had saved from his initial homestead construction, He filled a wooden bucket with clay chunks, carried the bucket up the ramp, dumped it, and returned for the next load. The process was inefficient and exhausting. He considered building a pulley system to lift buckets vertically, but decided against it. A pulley would save his legs, but require constant adjustment as the excavation deepened. The ramp was simpler and more flexible. Maintaining the dome curve while digging required constant measurement and adjustment. Lars carved a simple template from a thin board, a curved piece that matched the arc he wanted for his dome wall. Every few hours he stopped digging and checked multiple points against the template. Where the wall curved too sharply, he carved away more clay. Where it did not curve enough, he marked the spot and adjusted his digging angle. The process was tedious, but precision mattered. An irregular dome would have weak points where stress concentrated. A smooth, even curve would distribute forces uniformly. His grandfather's voice echoed in his memory. Measure twice, cut once. In this case, measure constantly, dig carefully. While excavating the chamber, Lars simultaneously began gathering stones for the interior lining. He needed hundreds of flat stones, each large enough to cover significant wall area, but small enough to handle alone. Dakota territory had no shortage of stones. Glaciers had left them scattered across the prairie in every size and shape imaginable. But finding the right stones required searching. Lars wanted pieces roughly the size of his hand to his forearm, flat on at least one side and reasonably straight on the edges. Rounded river stones would not work. They would leave gaps and create an unstable surface. He needed stones that could fit together like pieces of a puzzle, creating a relatively smooth interior wall. He found his best sources along the creek beds that drained into the James River 3 miles east of his property. Spring runoff had exposed fresh stones, washed clean and easy to evaluate. He spent his evenings walking the creek banks, selecting stones and piling them in locations he could find again. On Sundays, when he allowed himself a break from excavation, he hitched his wagon and hauled loads of stones back to his building site. Each trip brought 300 to 400 pounds of material. He made 8 trips before he had enough stones to complete the project. The stones piled up beside the excavation like a small mountain, gray and brown, and occasionally rust red, waiting to be fitted into place. Preparing the stones for installation required almost as much work as gathering them. Most stones had one good flat face, but irregular backs. Lars used a hammer and chisel to knock off protruding sections, creating backs that would sit flush against the clay wall. He did not try to make them perfectly flat. That would waste time and weaken the stones by making them too thin. He simply removed obvious protrusions that would prevent tight fitting. He sorted the stones by size and shape as he worked. Long rectangular pieces would work best for the lower walls where he needed maximum stability. More irregular pieces could go higher on the dome where the curve was tighter and smaller stones were easier to fit. Corner pieces and edge pieces got separated into their own piles. Organization now would save frustration later when he was working inside the chamber trying to find the right stone for a specific gap. The question of mortar troubled Lars throughout the preparation phase. Traditional stone construction used lime mortar to bind stones together and fill gaps. But lime was expensive on the frontier, requiring either transport from distant suppliers or time-consuming production from burned limestone. Lars had neither the money nor the time for proper lime mortar. He considered using mud, the simplest option. Mud would fill gaps and harden reasonably well, but mud would also absorb moisture, exactly what he was trying to prevent. Then he remembered something from his childhood in Norway. His grandfather had built a small storage shed using a mixture of clay, sand, and animal hair. The hair reinforced the clay, preventing cracking. The sand provided structure. The mixture, when properly proportioned and thoroughly dried, became nearly as hard as fired pottery and far more water-resistant than plain mud. Lars began experimenting with mortar mixtures in early June. He dug clay from the same layer he was excavating for the chamber, ensuring the material would bond well with the walls. Pure clay was too plastic, shrinking dramatically as it dried and cracking into useless fragments. He needed to modify its properties. Sand was the obvious first addition. He tried ratios from 1 part sand to 4 parts, clay up to equal parts of each. Too little sand, and the mixture still cracked. Too much sand, and it became crumbly, lacking cohesion. He found the best results at roughly 1 part sand to 3 parts clay. This mixture held together well and showed minimal cracking when dried in test batches. The animal hair addition required experimentation. His grandfather had used horsehair, but Lars had no access to enough horsehair for a project this size. He tried cattle hair instead, cutting it from cowtails and brushouts during grooming. The hair needed to be fairly short, about 2 to 3 inches long. Longer pieces tangled and clumped. Shorter pieces provided insufficient reinforcement. He added 1 large handful of hair to every bucket of clay-sand mixture, working it in thoroughly until the hair distributed evenly throughout. The effect was remarkable. Test pieces with hair could flex slightly without cracking. Pieces without hair were rigid and brittle. The hair acted like the reinforcing fibers in modern composite materials, though Lars understood it only as something that worked. He tried adding other ingredients based on vague memories and experimentation. A small amount of lime, purchased at considerable expense from a supplier in Yankton, improved water resistance but made the mixture harder to work. He used lime sparingly, adding just enough to give the mortar a slight chemical set, rather than relying solely on drying. He tried adding linseed oil, which made the mixture more waterproof but also greasier and slower to dry. He settled on a tiny amount, just a tablespoon per bucket, enough to provide benefit without causing problems. The final formula was approximately 12 parts clay, 4 parts sand, 1 part cattle hair by volume, plus small amounts of lime and linseed oil. The mixture had to be thoroughly blended with water to the consistency of thick porridge, then applied within a few hours before it began setting. Producing enough mortar for the entire project required planning. Lars could not mix all the mortar at once. It would set before he could use it. He had to mix batches as needed, which meant interrupting stone-laying work to prepare more mortar every few hours. He built a large wooden trough for mixing, using planks sealed with pine pitch to prevent leaking. He kept bags of prepared clay and sand nearby, pre-measured cattle hair in bundles, and his precious lime and linseed oil protected from moisture. Mixing a batch took about 30 minutes of vigorous stirring and kneading. The work was messy and exhausting, but the result was mortar that would bond the stones permanently while keeping moisture away from his meat. Every hour spent perfecting the formula was an hour invested in his family's survival through the next winter. By mid-June, the chamber excavation was complete. Lars stood at the center of a dome-shaped cavity carved into the hillside, 12 feet across and 8 feet high at the peak. The clay walls were smooth and even, following the curve his template had guided. Now came the most critical phase, installing the stone lining that would transform this hole into a functional preservation chamber. He started at the bottom, laying stones around the perimeter where the curved wall met the floor. These foundation stones were the largest and flattest he had collected. They needed to be stable because everything above would rest on them. He spread mortar on the clay wall, pressed a stone into place, then packed more mortar around the edges. The mortar squeezed out from gaps, which he smoothed with his fingers, creating a seal. The work proceeded slowly. Each stone had to be selected for its specific position. He could not simply grab any stone and force it into place. The curve of the wall meant that stones fitted at the bottom would not fit higher up where the radius tightened. He had to study each gap, then search through his sorted piles for a stone with the right dimensions and shape. Sometimes he found a perfect fit immediately. Other times he spent 20 minutes examining dozens of stones before finding one that worked. Occasionally, no stone in his entire collection fit properly. Then he had to take a promising candidate and modify it with his hammer and chisel, carefully knocking off sections until it matched the space. This trial and error process made progress maddeningly slow. On a good day, he installed 40 to 50 stones, covering perhaps 8 square feet of wall surface. The chamber had roughly 350 square feet of wall and ceiling to cover. As the stone wall grew higher, the physical demands changed. The first 3 feet were comfortable. Lars could work while standing normally, bending slightly to place stones and spread mortar. Between 3 and 5 feet, he needed to reach overhead, which tired his shoulders and made precise placement difficult. Above 5 feet, he could no longer reach from the floor. He built a simple scaffold inside the chamber, planks laid across wooden supports that he could adjust as the work progressed. Working from the scaffold was more dangerous. The platform was narrow and unstable. Mortar made everything slippery. He had to carry heavy stones up onto the scaffold, hold them in position with one hand while applying mortar with the other, then press them into place without losing his balance. Several times he nearly fell. Once he dropped a stone that shattered on the floor, requiring him to climb down, sweep up the fragments, climb back up, and start that section again. The dome's curve became tighter as he approached the top, which actually made the work easier in some ways. The steeper angle meant stones wanted to stay in place rather than sliding out before the mortar set. He could work faster because he did not have to hold each stone while waiting for adhesion. But the smaller radius meant he needed smaller stones, which took longer to install because more pieces were required to cover the same area. The final section at the top, roughly 2 feet in diameter, was the most challenging. He had to reach directly overhead while standing on his scaffold, fitting small stones into a circular gap while mortar dripped onto his face and arms. While the stone walls were curing, Lars turned his attention to the floor. Most root cellars and earth-sheltered structures had dirt floors, simple packed earth that required no additional work. But Lars wanted better drainage and thermal properties. Standing water would increase humidity and promote spoilage. He needed a floor that would shed moisture and provide thermal mass. His solution was a combination of earth and stone, similar to his wall construction, but optimized for different requirements. He began by digging out the existing clay floor to a depth of 6 inches across the entire chamber. This created a shallow basin that he filled with a base layer of gravel and small stones, materials that would drain water quickly and prevent capillary action from drawing moisture up from deeper soil layers. Over the gravel base, he laid his flattest stones in an irregular pattern, fitting them together as tightly as possible. Unlike the walls, the floor stones did not need mortar between them. Small gaps actually helped with drainage, allowing any water that entered the chamber to seep down into the gravel layer and eventually into the deeper soil strata. He chose stones that were roughly level on their top surfaces, creating a floor that was reasonably flat but not perfectly smooth. Some texture helped with traction. A perfectly smooth stone floor would be dangerously slippery when wet. He filled the larger gaps between floor stones with packed earth mixed with small pebbles, creating a surface that was stable and solid underfoot, but would not trap water. The result looked irregular and crude compared to a finished floor in a proper building, but it served his purposes perfectly. The smoke system required more planning than any other element. Traditional smokehouses used open fires or smoldering logs placed directly on the ground. Smoke rose naturally, filled the structure, and eventually escaped through vents in the roof. This method worked adequately in above-ground buildings where fresh air could enter through gaps in the walls. But Lars's underground chamber was nearly airtight. Without proper ventilation, smoke would fill the space completely, making it impossible to enter. With too much ventilation, smoke would escape too quickly, reducing preservation effectiveness. He needed controlled smoke generation and precise air circulation. His solution was a dedicated smoke pot, a cast-iron vessel he had purchased specifically for this purpose. The pot was 18 inches in diameter and 12 inches deep, designed originally for rendering lard, but perfect for generating sustained smoke from small amounts of fuel. He positioned the smoke pot in the center of the chamber floor, directly beneath the highest point of the dome. This location ensured that smoke would rise naturally up the curve of the ceiling and spread outward in all directions as it descended. He did not want the pot at the edge of the chamber, which would create uneven smoke distribution, with one side receiving more exposure than the other. The central position meant every piece of hanging meat would receive equal treatment. He built a small stone platform beneath the pot, raising it 4 inches off the floor. This elevation allowed air to circulate underneath, feeding oxygen to the smoldering fuel and preventing the pot from sitting in any water that might accumulate on the floor during humid conditions. The ventilation system required solving a complex problem. Lars needed smoke to stay in the chamber long enough to cure the meat, but he also needed fresh air to sustain the fire and prevent suffocation if he entered while smoking was active. Too much airflow, and the smoke would escape before doing its work. Too little airflow, and the fire would die or create dangerous conditions. He designed a 2-vent system based on principles he had observed in chimneys and bread ovens. The first vent was a small opening at floor level near the entrance, approximately 4 inches square. This would allow fresh air to enter and flow toward the smoke pot, feeding oxygen to the fire. Cold air naturally sank, so this low vent would create an inward draft without pulling smoke downward. The second vent was more complex. He needed an opening at the top of the dome to release excess smoke and prevent complete saturation of the chamber. But this vent could not be a simple hole. Rain and snow would pour through any unprotected opening. He created a chimney structure using a wooden box built from thick planks, 8 inches square and 3 feet tall. The box extended from the top of the dome upward through the earth and sod covering he would eventually install. Inside the box, he installed a wooden baffle, a horizontal piece positioned halfway up that forced air to flow in an S pattern. Smoke could escape upward, but rain and snow would hit the baffle and drain out through the small weep holes rather than falling directly into the chamber. At the top of the chimney, he built a simple wooden cap that protected the opening while allowing smoke to exit from 4 sides. Testing the ventilation required building a small fire in the smoke pot and observing the air patterns. Lars lit dry hardwood shavings and watched as smoke began rising toward the dome's peak. The smoke swirled along the curved ceiling, spreading outward in a mushroom pattern that descended slowly toward the walls. Some smoke found the chimney vent and escaped upward. Most smoke remained in the chamber, creating a hazy atmosphere that reduced visibility but was not immediately choking. He could breathe comfortably while standing in the chamber, though his eyes watered from the smoke. This was exactly what he wanted. Enough smoke concentration to cure meat effectively, but enough air circulation to allow him to enter and work when necessary. He adjusted the floor vent slightly, enlarging it by 1/2 inch on each side. This increased the draft just enough to keep the fire burning steadily without creating a wind tunnel that would clear the smoke too quickly. The final ventilation element was controllability. Lars needed to adjust airflow based on weather conditions and meat requirements. On humid days, more ventilation would prevent excessive moisture buildup. On dry days, less ventilation would maintain smoke concentration. He built simple wooden slides for both vents, pieces that could be pushed in or pulled out to partially block the openings. The slides were crude but effective, allowing him to fine-tune the system through trial and error once he began actual meat preservation. The entrance required careful engineering. This was the only opening into the chamber, the only structural weakness in an otherwise solid dome. Lars needed a doorway large enough to carry meat and supplies through, but small enough to maintain structural integrity and thermal stability. He settled on dimensions of 3 feet wide and 5.5 feet tall. This was barely tall enough for him to walk through without ducking, but larger openings would. Require more complex support structures. He framed the entrance with thick wooden beams, gray-weathered oak he had salvaged from a collapsed barn on an abandoned claim. The horizontal top beam was 8 inches square and 4 feet long, extending 6 inches past the doorframe on each side. These extensions rested on vertical beams that ran from ground level down to solid footings he had carved into the clay. The vertical beams were equally substantial, 6 inches square and 7 feet long. They ran alongside the entrance opening, anchored at the bottom in clay, and mortared in place with extra stone reinforcement. The weight of the earth above the entrance pressed downward on the horizontal beam, which transferred that weight to the vertical beams, which pushed it into the foundation. This post and lintel system was ancient technology, used in stone construction for thousands of years, but it worked perfectly for Lars's purposes. He wrapped the wooden beams with the same cattle hair clay mixture he had used for stone mortar, creating a sealed connection between the wood and the surrounding stonework. This prevented air gaps that would compromise the chamber's temperature stability. The door itself was Lars's masterpiece. He built it from planks milled from a single large cottonwood tree, wood that was dense and straight-grained. Each plank was 3 inches thick, cut to 5 feet long. He selected 7 planks, fitting them edge to edge to create a door 3 feet wide. Rather than simply nailing the planks to cross braces, he carved a tongue and groove joint along each edge. One side of each plank had a protruding ridge, the other side had a matching groove. When assembled, the planks interlocked mechanically, creating a solid panel that moved as a single unit. This joinery took him 2 full days to complete, working with hand tools to shape each tongue and groove precisely. The result was worth the effort. The assembled door had no gaps. Light could not pass between planks. Air could not leak through. He reinforced the door's interior face with diagonal iron straps he had forged himself, heating salvaged iron in his farm forge and hammering it into flat bars. The straps formed an X pattern across the door, bolted through the wood with hand-forged bolts. Each bolt passed completely through the door and was clinched over on the exterior side, creating connections that could not be pulled apart. The door weighed nearly 90 pounds when complete, but the iron reinforcement kept it from warping or sagging. He mounted the door on iron hinges, substantial pieces that he mortised into both the door and the wooden door frame. The hinges did not simply attach to the surface. They were set into carved recesses, then pinned through with iron bolts that passed through the frame into the stone and clay structure behind. The lighting system was Lars's most unexpected innovation. Traditional smokehouses were dark. Men entered with lanterns when they needed, to hang meat or check progress, then left. The idea of permanent lighting inside a smoking chamber seemed wasteful and dangerous. Open flames near wooden walls and hanging meat created fire risk. Oil for lamps was expensive. Why waste resources lighting an empty storage space? But Lars's design was different. His chamber had stone walls that would not burn. He needed to enter regularly to monitor meat condition and adjust smoking intensity. Working in darkness with only a handheld lantern was inefficient and dangerous. He could trip over the smoke pot, knock into hanging meat, or misjudge distances in the confined space. Permanent lighting would allow him to work safely and observe his meat's progress scientifically. He installed 2 small oil lamps on iron brackets mounted to the stone wall near the ceiling. The lamps were positioned opposite each other, roughly 8 feet apart, creating even illumination throughout the chamber. The brackets were simple, L-shaped iron pieces that he mortised into the stonework during wall construction, embedding them so deeply that they became structural elements rather than attachments. Each bracket held a small brass lamp, the type used in ship cabins, designed to burn for hours on minimal fuel. The lamps had glass chimneys that protected the flames from drafts while allowing light to spread. More importantly, the chimneys contained the flames completely. There was no risk of igniting anything unless the entire lamp tipped over, which was impossible given how securely the brackets were anchored. The lamp placement was strategic. By mounting them high on the walls near the ceiling, Lars put the light sources in the hottest, smokiest part of the chamber where smoke naturally accumulated. This seemed counterintuitive, but it solved several problems simultaneously. The lamps burned hotter in the rising heat, improving fuel efficiency. The smoke that concentrated near the ceiling actually improved lamp performance by creating a slight draft that fed oxygen to the flames. And most importantly, the lamps were positioned above the hanging meat, providing downward illumination that let Lars see every piece clearly without shadows. He could enter the chamber anytime, day or night, light the lamps with a simple match, and inspect his meat thoroughly. This capability transformed his chamber from passive storage into an active laboratory where he could monitor and adjust the preservation process continuously. No other settler had this advantage. Their smokehouses were black boxes, where meat either cured successfully or failed mysteriously. Lars built the meat hanging system during the last weeks of July. The racks needed to be strong enough to support hundreds of pounds of hanging meat, positioned to maximize smoke exposure, and easy to access for loading and inspection. He used seasoned oak poles, each approximately 3 inches in diameter and 8 feet long. The poles had to span the chamber without sagging under. Weight. Oak provided the necessary strength while being light enough to handle during installation. He stripped the bark completely, then sanded each pole smooth to prevent splinters from contaminating the meat. The smooth surface also made the poles easier to clean between smoking cycles. Dried meat residue and smoke deposits would accumulate over time, and Lars wanted surfaces he could scrub without creating hiding places for bacteria or mold. He installed 6 horizontal poles at different heights, creating 3 levels of hanging space. The lowest rack was positioned 5 feet above the floor, high enough to keep meat well above the smoke pot, but low enough that Lars could reach it easily while standing. The middle rack was at 6.5 feet, requiring him to reach overhead, but still accessible without climbing. The top rack was at 7.5 feet, just below the curve where the dome ceiling began to arch inward sharply. This rack would require a step stool to access, but it provided crucial additional capacity. Each rack could hold approximately 20 to 30 pieces of meat, depending on size, giving him total capacity for 60 to 90 pieces. This was far more than a typical smokehouse, which usually maxed out at 40 pieces before overcrowding compromised smoke circulation. The poles were supported at each end by notches carved into the stone walls. Lars had planned these notches during wall construction, leaving gaps in the mortar where poles would eventually rest. He carved the notches deep enough that the poles sat securely without sliding, but not so deep that they could not be removed if necessary. This removability was important. If a pole split or weakened, he could replace it without rebuilding the entire rack system. The notches also allowed him to adjust pole positions if he discovered that the initial spacing did not work as well as expected. Flexibility in the design meant he could adapt based on real-world performance rather than being locked into theoretical calculations. From each pole, Lars would hang meat using iron hooks he had forged from salvaged metal. Each hook was shaped like a simple S-curve, with one end looping over the pole and the other end piercing through the meat. He made 40 hooks initially, knowing he could forge more if needed. The hooks were not complicated pieces of metalwork. Any blacksmith could have made better ones, but they were functional, smooth enough not to tear meat fibers unnecessarily, and strong enough to support 5-pound pieces without bending. He hung the hooks evenly along each pole, spacing them about 8 inches apart. This spacing prevented meat pieces from touching each other, which was critical. Meat that touched would not cure properly in the contact areas. Smoke had to reach every surface. Adequate spacing ensured complete exposure. By early August, Lars's chamber was complete except for the final exterior covering. He had a functional smoking system, proper ventilation, adequate lighting, and sufficient rack space. He needed to test everything before committing his entire fall meat supply to an unproven design. He butchered a hog in mid-August, earlier than normal but necessary for testing purposes. The hog provided approximately 150 pounds of meat suitable for smoking after removing fat for rendering and bones for stock. He cut the meat into strips roughly 12 inches long, 4 inches wide, and 1 inch thick. These dimensions were traditional for smoked meat in Dakota Territory, large enough to retain moisture during the smoking process, but thin enough to cure completely in reasonable time. He prepared the meat with a simple salt cure, rubbing coarse salt into every surface and letting the pieces rest overnight. The salt would draw out moisture and begin the preservation process before smoking started. By morning, each piece was firm and slightly darker, with liquid pooled in the bottom of his curing crock. He rinsed the salt residue off each piece, patted them dry with clean cloth, and carried them to the chamber. Hanging the meat took an hour. He pierced each piece with a hook, ensuring the hook went through a thick section that would support the weight. Then he hung each hook on the lowest rack, spacing them evenly to prevent contact. 40 pieces filled the lowest rack completely. He hung 20 more on the middle rack. The remaining pieces went into his traditional wooden smokehouse as a control group. He would smoke both batches simultaneously and compare results. He started the fire in the smoke pot, using dry hickory chips. Hickory provided the classic smoke flavor that settlers preferred, slightly sweet and not too harsh. The chips smoldered rather than burned, producing thick white smoke that rose immediately toward the dome ceiling. Within minutes, smoke filled the chamber, swirling along the curved stone surface and descending around the hanging meat. Lars watched from the doorway, fascinated by the circulation pattern. The smoke did not simply rise straight up and escape through the vent. It spread outward along the dome, creating a horizontal layer that slowly descended like a fog bank, settling over a valley. Every piece of meat disappeared into the haze. He could see the glow of his ceiling lamps, but could not see individual meat pieces from the doorway. The smoke concentration was perfect, thick enough to cure aggressively, but not so thick that it choked him when he stepped inside briefly to check the pot. He maintained the smoke for 18 hours straight, adding hickory chips every 3 hours. The chamber stayed at a consistent temperature, approximately 60 degrees, based on the thermometer he had hung from the middle rack. His wooden smokehouse fluctuated between 45 and 70 degrees during the same period, responding to outside air temperature changes. By the second morning, the meat in his chamber had developed a dark mahogany surface, glossy, with deposited smoke compounds. The meat in the wooden smokehouse looked paler and less uniformly colored, with some pieces showing dark spots and others remaining almost raw-looking. Lars continued the test through August, monitoring both meat batches daily. After 5 days, the wooden smokehouse meat was ready by traditional standards. The pieces felt firm, smelled properly smoky, and showed no signs of spoilage. He moved them to his root cellar for storage, the standard practice. The chamber's smoked meat looked different. The surface was almost black, harder, and had a concentrated smell that was more intense than traditionally smoked meat. He left it hanging in the chamber for 3 more days, giving it 8 days of total smoke exposure. When he finally removed it, the meat was rock hard on the surface but still had slight give when pressed firmly. This was deeper curing than any smokehouse could achieve. The real test came in September when an unseasonable warm spell hit Dakota Territory. Temperatures rose into the 80s for 5 consecutive days, unusual for early fall, but not unprecedented. Lars checked both meat batches daily during the heat wave. The wooden smokehouse meat, stored in his root cellar, began showing problems by the 3rd day. Some pieces developed a slimy surface film. Others smelled slightly sour when he brought them close to his nose. The meat was not completely spoiled, but it was deteriorating. He would need to cook and eat it within days or lose it entirely. The chamber-smoked meat, which he had returned to the chamber after testing, showed no changes whatsoever. The surface remained dry and hard. The smell was unchanged. The color was stable. The earth-sheltered chamber had maintained a constant 55 degrees throughout the heat wave, while his root cellar had climbed into the mid-60s. Lars made his decision immediately. He would trust his entire fall meat supply to the chamber. If the test batch could survive a heat wave that damaged traditionally prepared meat, it could certainly survive normal storage conditions. He spent September preparing for the main butchering season. He carved additional meat hooks, bringing his total to 75. He gathered extra firewood and hickory chips for extended smoking. He cleaned the chamber thoroughly, scrubbing the floor stones and wiping down the walls to remove any residue from the test batch. He adjusted the ventilation slides based on what he had learned, slightly restricting the floor vent to increase smoke density. Everything was ready. When October arrived and neighbors began their annual butchering, Lars would be ready to preserve meat in quantities and quality that no traditional smokehouse could match. His family would not starve, not this winter, not ever again, if he could prevent it. October arrived with the first hard frost on the 7th. Settlers throughout the region began butchering their livestock, racing to complete the work before deep winter made outdoor labor impossible. Lars butchered in 3 hogs and 1 steer, animals he had raised specifically for this purpose. The work took 4 days with help from his brother Eric, who had recovered enough from his daughter's death to function, but remained withdrawn and quiet. They worked methodically, killing each animal humanely, bleeding it properly, removing organs and unusable portions, and separating the meat into categories. Some cuts would be eaten fresh immediately. Others would be salted and stored in brine barrels. The premium cuts, the meat that needed to last through spring, would be smoked. Lars ended up with 430 pounds of meat designated for smoking. This was an enormous quantity, far more than his test batch. He cut everything into uniform strips, applied his salt cure, and let the meat rest for 2 days. The curing process drew out moisture and began chemical changes that would help preservation. When he rinsed and dried the meat on October 10th, each piece was firm and ready for smoking. He began loading the chamber, filling the lowest rack first, then the middle rack, then the top rack. Every hook held meat. Every piece hung separately with adequate spacing. When he finished, 70 pieces of meat hung in the chamber, representing approximately 300 pounds. The remaining meat went into his wooden smokehouse and a neighbor's smokehouse insurance in case his chamber failed catastrophically. He lit the smoke pot at dawn on October 11th. The hickory chips ignited slowly, producing the thick white smoke he wanted. Within an hour, the chamber was completely hazed. He could barely see the ceiling lamps from the doorway. He maintained the fire continuously for 48 hours, sleeping in short shifts and waking every 3 hours to add fuel. His wife Margaret thought he was obsessed, staying awake to tend a fire that could be left alone. But Lars knew this initial smoking period was critical. The first 2 days determined how deeply the smoke compounds penetrated the meat. Inconsistent smoking now would mean spoilage later. He could not risk it. After 48 hours of heavy smoking, he reduced the intensity, letting the fire smolder with longer intervals between fuel additions. The meat had developed the deep mahogany color he wanted. Now it needed time for the smoke to continue working while moisture slowly evaporated. He kept light smoke going for 6 more days, checking the meat twice daily. By October 19th, the meat had been smoking for 8 days total. The surface was hard and dark. The smell was intensely smoky. He removed 1 piece and cut into it. The smoke ring penetrated a 1/4 inch deep, far deeper than traditionally smoked meat. The interior was still slightly pink but firm. This meat would last months without refrigeration. He left the remaining pieces hanging in the chamber with just a trace of smoke from a barely smoldering pot. The chamber would maintain perfect storage conditions even without active smoking. November brought the cold everyone expected, temperatures dropping below zero and staying there for weeks. Lars's chamber remained stable at 55 degrees, the earth insulation protecting it from the Arctic air above. He checked his meat weekly, entering the chamber with his ceiling lamps providing clear illumination. The meat showed no signs of deterioration. The surface remained dry. No mold appeared, no off-smells developed. His neighbors began reporting problems with their meat by late November. The same freeze-thaw pattern that had killed his niece the previous year was repeating. 3 days of relative warmth in mid-November, temperatures rising into the 30s, then plunging back to zero. Wooden smokehouses could not buffer these swings. Meat that had seemed fine suddenly showed surface moisture and discoloration. By December, several families had lost significant portions of their smoked meat. Anders Gunderson, who had called Lars's project wasteful, knocked on his door asking if Lars could spare any meat. His family had lost everything to spoilage and faced a hungry winter. Lars gave him 20 pounds, enough for 2 weeks if rationed carefully. He did not mention that his own supply remained perfect. Anders saw the meat quality and asked how Lars had preserved it so well. Lars simply said he had been careful with his smoking. He did not elaborate. The chamber remained his secret for now. Other neighbors came with similar requests. Lars shared what he could spare, never explaining his methods, but quietly noting who remembered his underground smoking idea and who had mocked it most loudly. January passed without incident. February brought another thaw, 5 days of temperatures in the 40s that destroyed whatever meat had survived the November cycle. By March, most families were surviving on dried beans, root vegetables, and whatever game they could hunt. Fresh meat was a rare luxury. Lars's family ate smoked meat twice weekly throughout the winter, rationing carefully but never going hungry. His chamber held its temperature through every weather extreme. The meat quality actually improved with time, the smoke flavor deepening and mellowing. By April, when spring finally broke winter's grip, Lars still had 120 pounds of perfectly preserved meat hanging in his chamber. He had started with 300 pounds in the chamber. His family had consumed 180 pounds over 6 months. Not a single piece had spoiled. In May, Lars invited several neighbors to see his chamber. They walked into the earth-sheltered dome, saw the curved stone walls and the ceiling lamps and the remaining meat hanging in perfect condition. No one laughed this time. Olaf Henriksen asked how long it had taken to build. Eric, Lars's brother, simply stood in the center of the chamber with tears running down his face, understanding that his daughter might have lived if this had existed the previous year. By June, 3 neighbors had started digging their own chambers. The impossible had become essential. Dakota Territory's preservation problem finally had a solution.